Okay, so today we are going to be talking about the ideal gas law with closed systems. So let's say we have a system right here, and part of it is filled up with water, and the rest of it filled up with air. Close it off. We want to know that if we increase the pressure from 101,000 pascals to 200,000 pascals, what the final temperature in this system will be. So to start off, that we know that we have zero point 0.1 meters cubed of the system's zero point 0.1 meters cubed, and then we know that the mass of the water inside of the system is 1 kilogram. The initial pressure, like I said, is 101,000 or 101,325 pascals. The initial temperature is 298 Kelvin. Um, the final pressure we want to increase it all the way up to 200,000 pascals, and then we want to know what the final temperature will be. So, since we have the closed system right here, the water's down there and there's up there. So we can apply the ideal uh, gas law, so PV equals nRT, where R is the gas constant, 8.314 joules per mole Kelvin. So how we're going to apply this is we are actually going to, all of these are going to stay the same. So the volume in the system stays the same. We're not going to be losing water, so the mass is still going to stay 1 kilogram. And then the N right here, the number of moles, that's going to stay true for the entire time. So the air inside of there, we're not going to lose moles of air somehow. So we know the final pressure that we're going to have. We know the final volume that we're going to have because we can figure that out, and we'll see how later. Gas constant stays the same, and then we're trying to figure out the final temperature. However, we first need to figure out the number of moles of air because we're not given that. We're only given the mass of the water and the volume. So what we're actually going to have to do is for this final pressure, we're going to have to, so the pressure is going to be made up of two partial pressures. One's going to be for air, and one is going to be for water. And what we can actually do with that, so we, with the last video we solved using Anton's equation, we can figure out like all like the different pressures and stuff from given data and everything like that. So the starting initial pressure is going to be the partial pressure of water at 298 Kelvin, and then the partial pressure of air we can actually figure out because we can again use this and say that the pressure of air is equal to, and then if we just take the volume and move it to the other side, the moles of air times the gas constant times the initial temperature, because we're for right now we're just trying to figure out the initial pressure of air, and then all that's going to be divided by the volume of just the air. Now we also don't know the volume of just the air, but we can figure that out because actually if we look, so we have a total volume of 0.1 meters cubed. So our total volume is going to be the volume of the air plus the volume of the water. Now, so then if we want to find just the volume of the air, we can take this to the other side and say that the volume, the total volume, minus the volume of the water equals that. So since we know the mass of the water, we can figure that out because we know the density of the water as well. So the volume of the water is going to be equal to the mass of the water divided by the density of the water. So there, now we know this and we have all the givens for that. So now we can, so now since we know the volume of just the air and we know the temperature and the gas constant, we can actually solve for the number of moles of air, because if we take this and plug it back into here, we know the initial pressure. So what we can do, let's rewrite this real quick. So the initial pressure is equal to the partial pressure of water at 298, which we know, so that's just a number, and then plus the number of moles of air, RT, over the volume of the air. So now we want to figure out how many moles of just the air that we have. So if we take the partial pressure of water and put it over the other side, we can say that the initial pressure minus the partial pressure of water times the volume of the air, and then divided by RT equals the number of moles that we have, or the number of moles that we're going to have. So now what we can do actually is we can go ahead and copy this equation from above. So since we know our final pressure, now we can plug in the found number of moles. So now our final pressure is going to equal the partial pressure of water at the final temperature, and then plus the partial pressure of air at the final temperature. So the number of moles of air, which is again going to stay the same, times R times the final temperature over the volume. Now, since we're going to be doing this in Python, the easiest way to do this is we can use a root solver, since we have both the final temperatures right there. We want to figure out both of the final temperatures, so we want to set this equal to 0. And I can just go ahead and show how this would work, what a root solver would do. So essentially what we're going to be doing, so let's say we just have like a random equation, so 5x cubed plus 4 divided by x squared. Minus. So we can see right here. So this equation, or this equation goes all the way down to 0 right here. So essentially what we're saying is, for this equation right here to equal 0, x has to be 0.969. But so again, we can actually put this in right here, and we get a straight line saying that x is always going to be, I guess I can't click it, but always the 0.969. So that's what we're going to be doing, is we're going to have when you have multiple x's set to equal to 0, you can find the root of that. So we're just saying we're finding where that equation equals 0. So if we go back, we want to set this equation equal to 0. So we're going to actually go ahead and move this to the other side. And so we have to subtract our final pressure and then set that equal to 0. And then when we put that in Python, we can take the root of that, and it'll give us our final temperature. Now, for the second part of this, actually, we are going to say, what if we do not have the given volume at the beginning? So we don't have that, but instead we say that at our final pressure of 200,000 pascals, we want a total of 0.3 moles of water vapor in the air, essentially. So realistically, I mean, we can apply all of this same technique, but instead of this now, if we go back down to here, so the total volume, we don't have just the total volume of air and water. We have to completely split it up now. So right here, our total volume of air, instead of subtracting the volume of water, because some of the water molecules are going to be in the air now, so this value is going to change. So what we are actually going to do is, since we know we have 0.3 we want 0.3 moles of water vapor in the air after at the very end, we can go ahead and say we want the number of moles of water vapor, so say NVW. So we'll take the volume of water, which is still just going to be this value right here, and we want to subtract the number of moles from that, but we can't just subtract the number of moles. We want the number of moles as a volume. So what we're actually going to do that is we're going to multiply the molecular weight, or molar mass, so mm, and then that just gives us grams. But if we go back up here, we can notice that everything is in kilograms up here. So what we're going to do is we're going to want to divide this by 1,000 to put this into kilograms. And then now we should have the correct volume of water in the system, or like after 0.3 moles have gone into the vapor phase. But now we still don't know what V total is. So we're gonna actually have to put in a second equation into Python and find the root for V total as well as the root for the final temperature. So if we go ahead and plug this back into here, so number of moles, so with partial pressure of water at the final temperature still, plus the all that, so that all stays the same. What we have to do actually is we have to change this volume down here. Okay. Okay, so actually to go back up here, we messed this up a little bit. So right here, you can see that I have the volume, the total volume of water, but we're subtracting a mass from a volume, which we can't do that. So what we're actually going to do is we're gonna change this to just the mass of water, and then we are going to divide this, because this right here is the whole total new mass. So then we're going to divide just this part right here by the density to get the new volume of just the water. So now what we have is, so we know we have a desired volume of moles in the vapor phase. But now we can actually figure out, well, quote unquote, figure out the real number of moles in the vapor phase if we just take the ideal gas law for just that. So if we do the partial pressure of water times the new volume of the water is equal to the number of moles of water and then at the final temperature. And then this partial pressure is at the final temperature as well. So we can, final temperature right there. So then what we can do to solve for this, for the number of moles, we can set that equal to the partial pressure of water at the final temperature times the volume of the water, which again we have right here. You can see behind the jumbled mess of writing, but then we divide that by RT, which with T being the final temperature now. So essentially what we have was we have a desired number of moles, and then we are going to find a given number of moles at the final temperature. So basically what we're saying is this number of moles right here is going to be equal to the desired number of moles of water, which is 0.3. So again, we can actually set this equal to 0. So we can say the desired number of moles minus the found number is equal to 0. And we're going to root solve for that as well in our Python code with the final temperature. And you might be, okay, well, we know that 0.3 moles is what we have, but what we're actually doing is we are solving for this right here, I believe. Yeah, we're solving for that right there, because to get the volume of water right here, we're just going back up through the list, and we have to it's going to initially take the root for, because this is our unknown variable right here, is the total volume. So what we're going to be doing is finding the root of this equation for the independent variable of the total volume, because everything else is known, because we're going to figure out the final temperature from the previous code that we will have. So then if we just add in another system, we'll say a system of equations, then we can find that we can find the total volume of the closed system if we want 0.3 moles in the vapor phase. So now if we get rid of this, go back to Desmos, I'll leave the site. So now I actually imported already, just to save time, the I cloned over the repository for all of the tools that we're going to need. So essentially what we're just doing is we're taking all of the chemical properties of water. So in here we have a nice list of everything, chloroform properties, everything else, but we're going to be focusing on water down here. So I mean, if we open that up, I mean, you can see we have everything that would ever be needed for the most part, all given values. So what we are going to want to do is get rid of this and then text. So first off, I'm going to want to import this into my code because we are going to be using this. So I'm going to import tools.che, and then also at the same time, I imported text, not code. Okay. Well, now we can import tools.che. I can spell tools right. And then also, to find the roots, we're going to do, we need the root from SciPy. So from SciPy.optimize imports roots. So then if we do that, can I import any roots? Okay, so I did figure it out. It is from the optimize library, it's root, not roots. So we can go ahead and redo that. So then now what we're going to want to do is we're going to want to take the content from the water properties. So if we do tools.che.props, and then I want to pass in water. So then now, okay, again. We'll figure this out. So the library is not called che dot, okay, it was a capital P. And then I want to pass in water. So now if we do that, it is not coming up again. Tools of CHE. I need to. Okay. So I do not know how to spell today or do anything. So it was a capital water, a capital W, not capital water. So now what we can do with this is we're going to start importing our initial values. So first we can say our total volume, so V total equals 0.1, and then our mass of the water, so mass of water equals 1 kilogram, and then the initial pressure was 101,325. 325. The initial temperature was 298 Kelvin, and then our R, which is the gas constant, is 8.314. So then if I do that, 1.325. So then now we can do that. So now what we want to do is we want to find the number of moles of air. Again, so we found that earlier. So the number, so N air is equal to it's equal to the initial pressure minus the partial pressure. Yeah, so, okay, yeah, so it's equal to the initial pressure minus the partial pressure of water. So if we go back up, so importing the properties of water, we can do P dot PVAP, so the partial pressure at the initial temperature, so TI. And then that should be closed off. Where it is. There it is. So, and then we're going to times that by the volume of the water. So it's going to be the mass of the water and then divided by the density of water. So if we do P dot and densities given by the letter rho. So if we do rho and then liquid of the initial temperature, so TI, so then that should all be closed off, and then times our R value, and then times our initial temperature value. So then if we do that, now we have the number of airs. I mean the number of airs, the number of moles of air in our code now. So now what we can do is we can start writing a function that we can take the root of. So if we do define, and then we can just call it any function. So we can just say of function Q. We want to pass in one variable, just call it, actually we'll call it X. And then if we do that, now we want our final temperature to be equal to, and what we're actually going to be doing, since we are putting in the final temperature into the actual code itself and then we're solving for that, we need to set it equal to almost like a spacer. So, and we're going to be returning it as an array at the end. So if we just say we're passing in X and then we want it the first index of the array, so then what we can do from there is to solve for that. We can pass in the volume. So now at the end, so what we're going to do is return what we want to solve for the root. So that's going to be the partial pressure of water minus the partial pressure of air, or no, not minus, plus the partial pressure of air minus the initial pressure. So we need to get those in here. So the partial pressure of water, so we can set that equal to and this is all going to be with relation to the final temperature. So what we're going to do is our properties dot the partial pressure, the partial pressure, so PVAP at the final temperature. So that's that, and then go back up, and then now we want the partial pressure of air. So the partial pressure of air is going to be the number of moles of air that we found out times R times the final temperature, and then all of that, just put in parentheses for good measure, divided by the volume of air, so, or the volume in the vapor phase. So now we need to do this for the volume of air. So we can say V air is equal to our V total minus our mass of the water, which is 1, divided by P dot rho L at the final temperature. So that'll give us the total volume minus the volume of the water. So then now we can shift enter that, and then if we do root dot Q, and then we pass in our an initial guess. We need to pass in a initial guess, so it's not that, it's root of Q and then an initial guess. So we can just say we'll put in the somewhere close to the initial temperature, so we can say like 300 Kelvin. So then if we do that and press shift enter, we get something. This needs to be capitalized, I believe. So then if we run that and then redo that, there we go. So our solution converged. So and then it gave us a value of that should, because now it's saying our temperature is around 0 Kelvin. So let's see, I must have messed something up here. Okay. Oh, okay. No, we do not want to. We want the final pressure, not the initial pressure. So let's go ahead and do this all again. So now again, it's giving me PF is not defined. I never even put it up here. So our final pressure is equal to very key steps. Okay, and then it messed up again. And then, so, and air. I spent about 10 minutes looking, and it was because I was not dividing by the R times the initial temperature. I was dividing by the R. I didn't have parentheses here, so I was dividing this by R and then multiplying it all by the initial temperature, and that was messing up all of this. So now if we look after we take the root, we can see that we get a final temperature of 366 Kelvin, just about. And that would make sense, because if we have a closed system, volume doesn't change, and we increase the pressure, the temperature's got to increase. So now if we move on to the second part of this, what we are actually going to do, so if we say we have a desired number of moles, so dN equals 0.3, and then we save that, we can go ahead and copy this, paste it down here, give it another, so equation QQ. So what we're going to do is, instead of returning just this, we also want to return a second equation, which is going to be our desired number of moles minus the found number of moles. So we'll just say NW, and then close that off. So then now we need to set a second x variable, so we can say that we want to find the total volume. So total equals x of the second index, so 1. And then now we need to manipulate everything here. So instead of just having the mass of water, we need, oh, not a 9, we need the mass of water minus the number of moles, so the desired number of moles times the molar mass of water. So we can do P dot molecular weight, and then divide that by 1,000 to convert it to kilograms. And then if we close it off, then we divide that by the density. Now our volume of all of the, it says air here, but all the volume of the vapor phase should now have changed. So now we need a separate variable now here to find the number of moles of water. So the number of moles of water is going to be the partial pressure of water, which we already have. So partial pressure of water divided by the volume of water. So that is going to be the same thing as up here. So we can just go ahead and copy this. So it's water times that, and then all of that. So I'll put that down here. What just happened? Okay, sorry, I was pressing Control instead. So then now we have the partial pressure of water, so the pressure times the volume of the water, and then now we can divide it by R times the final temperature, so T final, and then if we return both of those, we should get that. And then if we get a new line of code now down here, we can do roots of equation, the QQ equation, and then we need to have 2 initial guesses. So we can say, let's say, since it was close to 300, so 300 and so 300 and then initial guess of, I don't know, our first volume was 0.1. What did I do? Oh, the initial guesses need to go into the same column, I believe. Expected end. Close that off. Prop size, attribute, molecular weight. That needs to be capitalized. So there's that. So now if we run both of these, now we can say the iteration is not making good progress. So that means we need to have better initial guesses. So I guess we can say that's 366 and then the volume 0.1 again. So then if we run this again, process in the last 10 iterations, 0.01 maybe. Oh, no. Okay. Actually, I was doing this entirely wrong. It should not be the volume of the water. It needs to be the volume of the entire system of air, because we already have the volume of the water. So if we just do the air again, And then do that. See if we can run it again. Reached a maximum, so that's partial pressure water. How is this invalid syntax now? Let's see if we can get this fixed. So something is not working here. So let's see if I can get this figured out. So the problem here also was that I was putting in, so I changed it to 300. So if we go back to 366, which was the one temperature before, we can see that it says the number of calls to function has reached the whatever the maximum is for the root function. So if I put it back down to 300, then we can see that the solution converged, and it actually gives a final temperature of 326 this time, and about 0.6 or 0.06 of a total volume, so 0.06 meters cubed. And I believe because if you have that, so yeah, it's about 0.06. So this was the Python code for the ideal gas law with a closed system.